All right, so we're looking at systems of linear inequalities, part 2. And today what we're going to do is combine linear inequality systems with absolute value inequality systems. So as part of the warm-up, what I want you to do is graph each of these absolute value inequalities. And we're going to talk about their solutions and their equations and what they represent. So go ahead, take a minute and graph each of these inequalities. Alright, so let's look at each inequality graph. The first inequality is the parent function for the absolute value of x. It goes through 0, 0. Its slope is up 1 over 1. We can pick a test point, so I picked one below. I picked 1, negative 2. That test point turned out to be true, so I knew that this is where I needed to shade. So that y less than or equal to the absolute value of x is shaded below. The value of the line is solid, therefore solutions come from the line. Y greater than the absolute value of x minus 2 plus 4 is dashed because it's greater but not equal to. It is shifted to the right 2 and up 4. And if you pick the test point 0, 0 in this case, it turns out to be false. So we know we shade inside the absolute value. So we have the following problem that is an inequality word problem, in which we're going to investigate how to find solutions for inequalities with multiple parts. So it says Jenna spends at most 150 minutes a night on math and science. She spends at least 60 minutes on math. Write and solve a system of inequalities to model how she allots her time for the two subjects. So what we need to do is come up with variables. So we could say x is math and y is science. And we know that she spends at least 60 minutes on math. So we know that math is greater than 60. And she spends at most 150 minutes on math and science. So that means x plus y is less than or equal to 150. So I have a system of inequalities now. We have two equations representing these problems. So I'm going to label my x-axis as math. I'm going to label my y-axis as science. And if I go by tens, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, I'm 50 short, so I'll go by 20s. So 20, 40, 60, 80, 100, 120, 140, 160. And same with over here, 20, 40, 60, 80, 100. 120, 140, 160. So if I graph the inequality x plus y less than or equal to 150, I know I'm plotting my intercepts at 150, because if you plug in 0 for each, your x and y intercepts are both at 150. The slope is going down and over by 1, because you could subtract the x away. The line is solid. And then we connect our 2 points. Now this line is different from other lines we've graphed because this line has a beginning and an end at those 2 intercepts. So we don't put arrows implying they continue forever. It begins and ends with those intercepts, so we don't put arrows. And then we know that it has to be less than this amount of time, so we're going to shade below. But again, we also know that she can't study for 0 minutes, so we have to stop with the x and y axis. We're not shading out or beyond that triangle. So technically, there's 2 more bounds on this problem. There's the bound that she has to spend at, well, we know she has to spend at least 60. And for science, she can't spend less than 0. So we still need to graph the math x greater than or equal to 60. So 20, 40, 60, that's here. And what that means is that her math time can't be less than the blue line there. So her amount of time studying actually comes from this purpley blue triangle. An entrance exam has 2 parts, a verbal and a mathematics. For admission, the school of your choice requires a math score of 550 and a total score of 1100. You can score up to 800 points on each part. Write and solve a system of inequalities to represent this model. So, let's say x is verbal, y is math. Math has to be at least 550, so x is greater than or equal to 550. You need a total score of 1100, so that's x plus y. And you can score up to 800 points on each part. So what that means is that your y values have to be greater than or equal to 0 again, because you can't get a 0 or less on a test, but no larger than 800. And for the math, because the school has a minimum requirement, math has to be between 800 and 550. So let's graph each of these. So we said x was verbal, so we label the x-axis as verbal. y is math, so we label it as math. And then we're going to plot our points. So this time we can go by hundreds, so 100, 200, 300, 400, 500, 600, 700, 800. So we know that her verbal score can't be over 800. So we're going to draw in a line here. That means the x-intercept is 800. And our shading would be to the left. We also know that her score can't be less than 0, so we use the y-axis as a second bound. And then we're going to plot our math lines. So we know that math has to be greater than or equal to 550. But has a maximum of 800. So now we're minimized or locked into this yellow rectangle for where her scores can be. And then our final requirement is that it's greater than or equal to 1100. So we're going to plot our y-intercepts. So 8, 9, 10, 1100 would be up here. And again, we know she has to score higher than that. So that means she has to score within the yellow line, the black line, and the blue line. So her scores on the SAT have to come from this trapezoid that is kind of a grayish black. And then again, like I said in the warm-up, we are also looking at linear inequalities with absolute values being graphed. So the last few days we've focused on graphing linear inequalities, and 2 of them at the same time. Now we're going to focus on graphing a single linear inequality and an absolute value. So let's start with the red graph. We have y greater than or equal to 3. So a line that is y greater than or equal to 3 is horizontal. It has a slope of 0. And that means that we are shading above because y is greater than. And then we have the absolute value equation, y greater than negative absolute value of x plus 2 plus 5. So the plus 5 tells me up 5 units. The plus 2 inside tells me it moves left 2 units. And the negative tells me it is reflected or opened down. The inequality is greater than, but not equal to, so my absolute value is dashed. And the y values are greater than, so here's my vertex, so that means the y values are greater than above the absolute value. So that would be everything above it. So my solution set will come from where both the red and the blue overlap, or the purple. And again, when you're doing this on a test, you want to make sure I know whatever region is darker. So if you don't even want to shade where that blue is, that is perfectly fine. As long as I can tell that this region above the red line and above the absolute value is the darker or purple area, then you're good. So again, you don't have to shade this region in here. Oops, did I just change the color? So if you didn't shade that part there, that's perfectly fine. And you only shade above, that works. Okay, next we have y greater than or equal to x. So this goes through the origin. Our slope is +1, up 1. My line is dashed, or sorry, my line is solid because it's greater than or equal to. And we shade above because it's greater than. And then next we have y less than or equal to the absolute value of x plus 5 minus 2. So it is going to be to the left 5 and down 2. It is open up. And my graph is solid. The y values are less than, so that means I shade below the absolute value. And again, I'm already bounded by the red equation, so I'm going to stay between the two lines and kind of get that Nike looking swoosh. So my solution set comes between the two graphs. So similar to the verbal equations, we can do something called find the coordinates of the vertices of the figure. So that's kind of what we are looking at with our word problems. So we were graphing lines. So in this case, y is less than or equal to 6. So you would graph your first line. It's shaded below. So you would do that really lightly in your pencil. Then you have the next bound, x is greater than or equal to -4. Do it a little lighter just so I can plot my other points. And then we have the line y greater than or equal to -2 plus x. So that tells me my y-intercept is at -2. and my slope is positive 1. The line is solid. There we go. And it's shaded above. And then last we have y plus 2x is less than 7. So we'd have to subtract over that 2x to get this in y equals mx plus b form. So we'd have y is less than or equal to negative 2x plus 7. So plus 7 is my y-intercept. And then it's going down 2 and over 1. And the y values are less than that. So that means we would shade below the line, which means my solutions come within this shape here. It asked me to find the coordinate of the vertices of the figure. So the coordinate of the vertices are all the points of intersection. So that's this point right here. So that's at negative 4, positive 6. So we're going to have 4 coordinates in this case. So one coordinate is at negative 4, positive 6. We have another coordinate here where the black, or the y less than or equal to negative 2x plus 7, intersects the y less than or equal to 6. So that coordinate appears to be at 0.5, comma, and again, the y value is 6. You could check that by plugging in 0.5 to the purple equation to see what it is. So negative a half times a half, or negative 2 times a half is negative 1. Negative 1 plus 7 is 6, so we know we got that right. And then over here, the next easiest point is to look at where the blue, or the negative 4, intersects the other equation, y greater than or equal to x plus negative 2. And again, it appears or looks like they intersect at negative 2, 3, 4, 5, 6. And you could check that by plugging negative 4 into the equation. So negative 2 and negative 4 give negative 6. And our last point of intersection is where the two y equations meet. And it appears they meet at 1, 2, 3, 1. And again, you could check that by plugging in 3 for x, so negative 2 plus 3 is in fact 1. So we have 1, 2, 3, 4 vertice intersections. Okay, so your next assignment is the next page in our notes guide packet 433. So you go ahead and work on that now.